So this is going to be our first lesson into this entire year-long study of calculus. And I think it's important before we just dive right into the notes and start talking about just some examples about what calculus is and what you guys are going to be kind of expected to do. And calculus is really the study of how things change over time. So time is always changing, and then how do things change when time changes? And a couple of big topics we're going to get into in this course is this. I'm just going to talk about kind of the two main issues of calculus. Well, three now, if you're in BC here. And so the first one, we're going to say, okay, let's say you don't need to write any of this down. Just kind of listen here. So the first one is, the whole first semester of calculus is all about slope. And what we're going to be trying to do is find the slope of a line that is tangent to a graph. Now think about your studies of slope. Slope has always been, well, you take 2 points and you do rise over run, right? You do y2 minus y1 over x2 minus x1. Well, if you're trying to find the slope only at 1 point, well, now you can no longer apply this formula. And so this is where calculus is going to come into play. And we're going to start off with a little exploration at how we're going to attack that first big idea and big question of calculus. Is how do you find the slope of a line if you only know 1 point? And so that's going to be kind of the beginning of our discussion today. The second part of calculus, which we don't start for quite a while, is you guys know how to find areas of circles and rectangles and squares and rigid shapes from geometry. But the second big thing of calculus is, okay, if you have some big messy function like this, how do you find the exact area underneath that curve? Because we have no way of calculating areas given these messy curved lines right here. You've never learned a formula for that. And that's going to be the big second study of calculus. And then, since we're talking about BC here, if this is a BC lesson, because I never know who's going to be watching these lessons, BC, the second semester of BC, gets into series. And you should have seen or remember this from Algebra 2, if not pre-cal. And the big third thing of calculus in BC is, how do you know if when we add a whole bunch of numbers together, like 1 plus 1/2 plus 1/3 plus 1/4 plus dot dot dot, how do we know if that's actually going to tend towards some number? Where if we end up getting numbers really minuscule at the end, that we're going to kind of get really close to an exact value. We call that convergence versus divergence. So here's kind of the three main issues that we're going to be studying in this course. Okay. Now let's go ahead and I want you guys to open up your book. When we're doing these lessons, I want you guys to have your calculator ready especially. And then this first thing in our notes right here, there's an exploration that we're going to be doing, kind of exploring this first topic of calculus. And so what I've done, and I'll kind of put this book right here also for the exploration. So I want to explain this really quick, and then I want you guys to pause it and then do this exploration, okay? So I mentioned how we're going to be trying to find the slope of a tangent line. Well, the way we're going to approach this is, if you knew 2 points here and here and found the slope between them, well, this slope of this blue line is not very close to the slope of this line that we want. But let's say we take that second point and move it a little closer to the point that we want the slope of the tangent line. And then we calculate the slope between those 2 points. Well, that slope is still not very close to the one we want. Well, if we move it closer and closer, so say right here, well, this slope is getting a little closer to the slope that we want, but what if we move it even closer right here and then calculate that, or even closer? And that's what this first exploration is going to be doing, okay? So they have this function, y equals x squared, and you don't really have to graph it. I kind of have a rough sketch on the note outline. And what they want you to do is they give 5 different ordered pairs. And it says each successive point gets closer to the point 1, 1. And they want you to find the slopes of the secant lines through Q1 and P, and then through Q2 and P, and Q3 and P. So basically you're doing the slope formula 5 different times. Now notice they didn't give you the y values here, so just to save time on the note outline, I just have already calculated the y values of those x values. So I have Q1 at 1.5, 2.25. And so what I want you to do is pause the video and I want you to find the slope between all 5 of these ordered pairs. So go ahead and pause, take out your calculator, and you could just use your calculator. You don't need to show any work, and go ahead and do this. Okay, so you should have gotten, if you calculate the slope between P and Q1, about 2.5. So you do 2.25 minus 1 over 1.5 minus 1. You're just doing the slope formula. If you calculate the slope between P and Q2, you should get about 2.1. And then 2.01. And then 2.001. And then 2.0001. And what's happening is this. Okay, if I would, this is going to be not a great sketch over here, but if I would roughly sketch the graph of x squared, okay, and P is at 1, 1. So let's say 1, 1 is right here. What's happening is Q1 is right here. So when we calculate the slope between P and Q1, we get 2.5. And then we move Q2 a little closer, and we get a slope of 2.1. And then we move Q3 a little bit closer, and that slope would be 2.01. And then Q4 is even closer, and then Q5 is even closer. And so you can get a visual here. If we would calculate the slope or draw the secant line between these 2 points right here, that would be almost the exact same slope, and it would look the exact same if I would draw the tangent line to that point right there. So the closer you bring that second point to the point that you're analyzing, the more accurate your slope is going to be. And so right now, we don't have a way to find the slope given 1 point, but we kind of just did. We're noticing that if the second point gets really close to the first point, we're tending towards, or we say we're limiting towards, because this whole thing is about finding limits, we're limiting towards a slope of 2. So we could even say, what is the slope of the tangent line at P? Well, it's 2. And we'll have analytic ways of finding that, but that's the whole main idea of this first branch of calculus. How do you find the slope of a tangent line? And then it says, what is the equation of the tangent line at P? So now we have to remember how to find equations of tangent lines, or equations of lines in general. Anytime we want to write the equation of a line, regardless of what you learned in pre-cal, I don't know who teaches what anymore, but I do not want you to do this. I don't want us to do this and then plug in x, y, and m and find b. Okay, so I want to nix that from your skill set. It's not technically incorrect, but this whole study of calculus is about slopes at points, at exact points. And so the method that we're going to be dealing with is called point-slope form, which I know I taught you if you had me in Algebra 2, if you had Algebra 2 honors. And I think this is the only way they teach it in Algebra 2. But I think in pre-cal, Mr. Porter might do this, or whoever your pre-cal teacher is might do this method. Okay, so now we're going to take the point that we're dealing with. We want the tangent line at P. And we know the point at P is 1, 1, and we know the slope is 2. So y minus 1 equals 2 times x minus 1. You don't need to simplify that. You don't need to put it in slope-intercept form. You need to know how. We'll get into lots of discussion on AP tips and tricks and multiple choice questions versus free response questions. We'll get into all of that. So when you guys are doing your homework, I would check all your answers. And you might get answers that are equivalent to the back of the book. I would encourage you to try to get to the back of the book answer just to work on your manipulation skills. Because oftentimes when you take multiple choice questions, you might get the right answer, and then their choices might not be the one that you got, and you have to know how to manipulate. So just practicing those skills. But for this one is absolutely fine. Okay, so let's dive into another talk here about domain. So we have a function, x squared minus 25 over x plus 5. And we've studied rational functions quite a bit. It says, what is the domain? Now think about what that's asking you to do. It's saying find what you're allowed to plug in for x that gives you a defined real number value. Well, I could plug anything in the world I want in for x. I could plug 1 in, I could plug -6 in, except there's one number I can't plug in for x. Think about what that number would be. And hopefully you came up with -5. You can't plug -5 in for x because that would give you a 0 in the denominator here. So we say the domain is all real numbers where x does not equal -5. That's our domain. So x is not allowed to be -5. We can't plug -5 into this function. But what I want you to do is take your calculator And I want you to graph this function. Now remember, when you graph, oftentimes you need to put parentheses around your entire numerator and denominator to get it to graph exactly what you want. So I want you to graph this function. And what does the y value appear to equal when x is negative 5? Now y can't be anything at negative 5 because it's not in the domain. But what does it look like it is? So go ahead and graph that. I'll wait and just sip on my coffee. We had a 2-hour delay today. I came in at 7 still just to make these videos, so I thought I'd stop and treat myself to some coffee. Alright, so hopefully you have this graphed, and you look at your graph, and when x is negative 5, the y value appears to be negative 10 on your graphing calculator. Now that's impossible. It's impossible for there to be a point at negative 10, and I want you to think about why. Think about what you've learned about rational functions, about why there is no value at negative 5 and exactly what's happening at negative 5. What's happening at negative 5? Some of you might first think, well, I remember talking about if your denominator is 0, then there's a vertical asymptote. And you'd be on the right track, but there's two differences about what happens when your denominator is 0. So I want to talk about that real quick. If I gave you a function like x plus 1 over x minus 3 and said graph this, now you don't need to, but there would be a vertical asymptote at x equals 3 because 3 makes the denominator 0. However, there's not going to be a vertical asymptote on this one because we can actually factor the numerator. It's a difference of squares. And any factors that cancel creates a hole in the graph. So this function is actually the line y equals x minus 5, except, so I'm going to graph this really quick. So slope of 1, and I'm not going to graph this whole thing, but slope of 1, and then it's going to be a line like this. Except when x is negative 5, there's going to be a hole in the graph right here. Now your calculator doesn't really show them, but that's what's happening right there, is there's a hole when x is negative 5. Okay? But this whole study of limits is all about what is happening as you approach a certain point. It's not about what is happening at a certain point. And that's going to be a big topic and a big concept for the study of limits. What is happening as you approach a point, not what is happening at a point. Okay? So let's look here at example 2. Now I'm going to read this and kind of explain the notation and what this is asking you to do. So the way this is read, this is saying find the limit of the square root of 1 minus x minus 2 over x plus 3 as x approaches negative 3. Okay, let me say that again. The limit of this function as x approaches negative 3. Meaning we don't care what happens at negative 3. In fact, if you plug negative 3 into here, you're going to get something that's undefined. If you would make a table of values in your calculator, like we're going to look at right here, this is going to turn out to be undefined. But we don't care about that. We care about what is happening as x approaches negative 3. So what we need to do is this. We need to think about what's happening as x approaches negative 3 from the left. Now when I say negative 3 from the left, that means from x values to the left of negative 3, so less than negative 3, and we're going to look at what's happening as x approaches negative 3. We're going to get values really close to negative 3, okay, and see what happens to the y value. Then we need to find the limit as x approaches negative 3 from the right. Let's see what happens as we approach negative 3 from the right side. Let's see what happens to our y values. And let's see if these are approaching the same number from the left and the right. That's what we're hoping is going to happen. We'll talk about what happens if it doesn't, okay? So what we do is take our calculator, and you don't need to plug in these for x right here. What I would do is enter this in y equals, and then just go to your table. And remember, in your table, if you want to be able to put x values in, go to table settings, which I'll pull my calculator out and show you. So if you want to do this, you go up to table settings right here, so second window, and you want your independent. I almost always have my independent set to ask. I'm not sure why it's not right now, but I want it to go to ask. Now when you go to your table, it's going to let you plug in these x values that you see right here, okay? And you might want to pause this and practice this because I do find that some students struggle with inputting these functions because the functions we study in this class are just going to get messier and messier. So it's important to know how to work your calculator and parentheses and all that. But anyway, when I plug these values in, here's what I get. I get negative 0.24845, negative 0.2498, negative 0.24998, error, because you can't divide by 0, negative 3 is not in the domain. On this side I got negative 0.2500, and all of our calculators are going to give us something a little bit different, especially when we're dealing with numbers this small. Negative 0.25015 and negative 0.251582. I'll give you a second to jot those down if you haven't already. And I want to explain what we're after here. When we're talking about limits, we do not care what is happening at that particular x value. We care what is happening as we approach that value from the left and from the right. Are the y values getting closer to any certain number? That's what we're after. And you can kind of use the eyeball test here, and this is our first analyzation of doing a limit. We're going to have various ways of evaluating limits, okay? But this is the very first method. You can create a table and just see if your y values are approaching something. And if I look here, as we approach negative 3, well, I should say as x approaches negative 3 from the left, we're getting really close to about negative 0.25. And as we approach negative 3 from the right, we're getting really close to about negative 0.25. In fact, we got there on this side. Here's our notation, okay? Since the limit, and we're going to have to be very good with notation in this class. If you're someone who you haven't really been neat and organized with your work and showing work, now's the time to fix that because you get a lot of points for showing nice, neat, clean notation work. And you get dinged a lot of points if you're not very good at expressing yourself mathematically. So we need to be good at this. So since the limit as x approaches negative 3, now the way we say from the left, we put a little minus sign up here in the top right corner. This is standing for the limit as x approaches negative 3 from the left. Now that limit, and we got to put the function in there. So the limit of the function as x approaches negative 3 from the left is equal to negative 0.25, which is also equal to the limit as x approaches negative 3 from the right for that function. So I want you to look at this notation here. The limit of the function as x approaches negative 3 from the left is equal to the limit of a function as x approaches negative 3 from the right. In order for a limit to exist, the limit as you approach that value from both sides has to be equal. Okay, let me say that again. Your limit as you approach from the left and the right have to be equal in order for a limit as you approach that number in general to even exist. And if they are the same, like this is the same, then I can make the claim. So since this is true, the limit as x approaches negative 3 of square root of 1 minus x minus 2 over x plus 3, in fact equals negative 0.25. Even though the function itself doesn't equal anything at negative 3, the limit, the y value, as we approach negative 3 from both sides is tending towards negative 0.25. All right. So again, the limit does not depend on what happens to the function at x equals c, c being our target x value, but what happens as we approach c from the right and the left. So I have a messy looking function over here. I've called it f of x, and I don't know what this equation would be. But that's irrelevant. We're just going to use the vocabulary to answer these questions over here. So it says, what is the limit of this function as x approaches a? All right, so the way we attack this, we have to approach a from the left and the right. All right, so I look at when x is a, and I trace along the graph. So I'm going to approach a. It's like I'm walking along this graph, approaching a. I'm walking on the graph, approaching a from the left. And I look at what y value I'm getting really close to as I approach a. I don't care about what happens at a, but as I approach a from the left, I'm getting really close to this y value of L right here. So I would say the limit of this function as x approaches a from the left is L. I'm going to write that down. the limit as x approaches a from the left is L. Now I need to approach a from the right. So I come on the right side of a and approach it from the right. Walking along, wonder what y value I'll get to. And I approach L again. So that equals the limit as x approaches a from the right. So since the limit of the function as we approach a from the left and the right is equal, and it's L, then the limit as x approaches a in general is L. So we have to analyze both sides. What is the limit of the function as x approaches b? Well, let's approach b from the left. As we approach b from the left, we're getting really close to this y value of m. In fact, we get there, but that's irrelevant. M. So the limit of f of x as x approaches b from the left equals m. But as we approach b, so we still have to be on the function. So as we approach b from the right, notice now I'm on this part of the curve, I'm approaching this y value of k. So I would say the limit of f of x as x approaches b from the right is equal to k. So since the left-sided limit and the right-sided limit aren't equal, then this limit as x approaches b does not exist. There is no limit as x approaches b. They have to be the same. I kind of call it like the finger test. If you put your fingers on both sides of the x value you're dealing with and approach, your fingers should touch as you get to that value. And that means the limit is wherever your fingers are going to touch. But as I approach b from the left and right here, my fingers are kind of disjointed. They're not going to touch. The limit doesn't exist. And so we use a little acronym of does not exist, DNE. And for those of you that have ever seen the movie Mean Girls, she wins the competition at the end by saying this answer. This is what she was referring to. They ask her a question, and she says, the limit does not exist, and that's what she's talking about. Now, I said add this question. So I also want us to be able to analyze and understand the difference about when we care about what's happening at an x value versus approaching an x value. If I say, what is f of b? So I look here, I care about the y value of this function when x is b. I can answer this question, even though the limit doesn't exist as x approaches b. F of b, now this is where open and closed circles come into play. F of b is actually m. It's that closed circle right there. So f of b does exist, even though the limit itself doesn't. Just like over here, f of a doesn't exist, but the limit does. So it's important to understand concepts in this class about what it means to limit towards and what it means to be equal at a certain x value. All right. I hope this is recording well. I would hate to do all these notes and then something screw up. I guess we'll find out at the end. All right, find the limit of this function. Oh, we have a lovely piecewise function. So I want to find the limit of this function, this piecewise function, as x approaches 1. All right, I want to know the limit as x approaches 1. So I said option 1 is create a table. All right, you can make a table and analyze the table. Option 2 is to sketch a graph. Sketch a graph and see what happens. Let's graph this piecewise function. Okay, and these are things that we need to be pretty good at without me reteaching a whole bunch of previous skills. So we should be pretty good at sketching a piecewise function. So I'm going to do this. And if we're not, then I would suggest, watching a few more YouTube videos on other topics if we're talking about things that, it's a little bit of a struggle. So I want y to be 3 everywhere except x equals 1. So this is the horizontal line y equals 3, except at 1. So at 1, 3, there's a hole. So it's line y equals 3 everywhere except at 1. That's the first piece right here. And then the y value equals 1 when x is 1. So they're giving me a point right here. They're saying only at x equals 1, the y value is 1. So at 1, y value is 1. There's a point right here. So there's the graph of this piecewise function. But we want the limit of this function as x approaches 1. So we need to approach 1 from the left, and we need to approach 1 from the right. So let's do that. As we approach the x value of 1 on the curve from the left, think about what y value we're getting really close to. Well, we're really getting really close to this y value of 3. And as we approach 1 from the right, we're getting really close to a y value of 3. Again, does not matter what's happening at 1. So we say, since the limit as x approaches 1 from the left, and always make sure you put the function inside here. I find a lot of students won't do that. Make sure you always say the limit of what as x approaches whatever. Well, that equals 3, which also equals the limit of the function as x approaches 1 from the right. We have to get very comfortable with writing notation out. Since this is true, the limit of f of x as x approaches 1 in general equals 3. All right. Let's do the next one. You might want to try this one on your own. I mean, if you want, go ahead and pause it. If you got time and you want to get away from Netflix for a little while, go ahead and pause this, try this out. But I'll go through it as well. So we're going to graph this again. I want to find the limit of this function as x approaches 0. And I try to attack as many questions as I can without a calculator, because on the AP exam, you only get a calculator on a third of the exam. 15 multiple choice questions and 2 free response questions, you get a calculator. 30 multiple choice is non-calc and 4 free response is non-calc. So a lot of it is non-calculator. We will discuss a whole bunch of stuff with the calculator, but a lot of it is non-calc. So we're going to go ahead and graph this. And think about how you can graph anything in the world. I don't know what this graph looks like, to be honest with you. We don't discuss this. No, you should know what y equals x squared looks like. You should know what absolute value of x looks like. You should know what the square root graph looks like. You should know all those things. But this is not one that is really taught. It's not a parent function. So we make a table. Let's make a little table of values to graph this, okay? So let's say x is, I'm just going to pick some numbers. And let's see what the y value would turn out to be. And we can use a table to create graphs. So if I plug negative 2 in for x, I'm going to get positive 2 over negative 2. So negative 1. If I put negative 1 in for x, I get 1 over negative 1. If I put 0 in, well, 0 over 0 is undefined. If I put 1 in, we get 1. And if we put 2 in, 2 over 2 is also 1. So what this is showing is anywhere to the left of 0, any negative x values, our y value will be negative 1. So right here. And anywhere to the right of 0, our y value will be positive 1. But at 0, it's undefined. But we can't just start our line and then just draw it. We need to put open circles, signifying kind of a boundary, and also it's not inclusive right there. So the bottom piece is going to look like this. Top piece like that. There's our graph, just from sketching a little table. And the question says, find the limit of this function as x approaches 0. So we need to analyze from the left and from the right. So the limit as x approaches 0 from the left is negative 1. The limit as x approaches 0 from the right is positive 1. So since they're not equal, the limit does not exist. But I'm going to write out this notation. The limit of absolute value of x over x as x approaches 0 from the left equals negative 1. The limit of absolute value of x over x as x approaches 0 from the right equals positive 1. Since the left-handed limit and right-handed limit are not equal, we say the limit as x approaches 0 of absolute value of x over x does not exist. We don't really say equals does not exist, we just say the limit does not exist. All right. 5. So we have a graph here, and you notice that there's a vertical asymptote right here as x is approaching 2. We have some sort of vertical asymptote, so find the limit. Well, this is where things get a little bit hairy. So a limit should be a number. It should limit towards something. And so actually anytime you are approaching infinity, like your y value is approaching infinity, technically the limit does not exist. However, normally when these questions are asked, they're asking about graphical behavior. And so there is a difference between your graph approaching positive infinity or tending towards positive infinity versus negative infinity. So what I mean by that is this. The question might say, what is the limit of g of x as x approaches 2 from the left? And what I've been told, this is what I've been told from people that go out and grade the AP exams, oftentimes when they're asking for a limit in general and the answer is infinity, they're looking for does not exist. But if they're looking for one-sided limit behavior like this, they actually want the answer infinity or negative infinity because they want to know what is the graph actually doing? Why does it not exist? So as x approaches 2 from the left, this graph is going down forever. It's unbounded, going towards negative infinity. So you'd say this is negative infinity. And the whole concept of calculus, as you'll see as we go through the course, deals with this notion of infinity, that it's not something that we should be scared off from, that we can actually write answers like this. And if it said, what's the limit as x approaches 2 from the right? Going up to infinity and beyond. There we go. But you may look in the back of the book and it might say does not exist because technically a limit is supposed to be a number. Okay. What I've been told on multiple choice questions, they will never pit these two answers against each other. Like they'll never make you make the decision, do they want me to put infinity or does not exist? They'll never ask you to do that. So it'll be one or the other. And my guess is they would care more about do you understand the behavior. So I think it's more important to understand this, but also understanding why in the back of the book it might say does not exist. This one's really similar. So 1 over x squared looks like that volcano graph. It's got a horizontal asymptote here, which we'll discuss horizontal asymptotes a little bit in this class. And a vertical asymptote is 0, and it looks something like this. And so as x approaches 0 from the left, it's going up to infinity. And as x approaches 0 from the right, the function is going up to infinity. The function still does not exist, even though both are approaching infinity. So the reason this one wasn't, okay, I should say this. This was not does not exist because one was going towards negative infinity and the other one positive. This answer still technically would be does not exist, even though both sides are going up to infinity. But again, oftentimes the question they'll ask you is about one-sided limits, and so that answer you would probably want to put infinity. All right, I want you to graph, take out your calculator, and we got a couple more. Graph y equals cosine of 1 over x. And in this class, we're always going to make sure that we are in radians. Our mode needs to be in radians in this class. If you're in physics C, I think you're in degrees quite often. And so to jump back and forth between the classes, you're going to have to change your modes a decent amount. So I want you to graph this. And it's not really going to look like anything crazy at first. I'll graph it too. So right here. And we want the limit as x approaches 0. So I look here, and we can't really tell. It kind of looks like maybe that y value right down there, but I don't really know. So we're going to go ahead and zoom in. So I want to zoom in here. So we push zoom in. And remember, to zoom in, you actually have to push enter one more time. And that looks interesting. So it did some sort of wave right here. So I still don't know. It's looking really crazy. Let's try zooming in again. Maybe we get a better picture. And it got worse. This is called oscillating. When you kind of squeeze in here between these two x values, whatever they are, this graph just starts to go really, really crazy. And this is a case where the limit also does not exist. I'm going to talk to you on the back here about the 3 times limits don't exist. This is one of them. If you have a graph that oscillates as you zoom in farther and farther, the limit does not exist. And again, that's called oscillation. Okay, so there are 3 times limits do not exist. And I'll have you jot down. So when we say a limit of a function as x approaches c does not exist, one of 3 things could be happening. The function does not approach the same number from the left and right as x approaches c. So that's kind of where we do the finger test if our fingers don't match up. A function increases or decreases without bound, so some sort of vertical asymptote going towards infinity or negative infinity. Or if our function oscillates between two fixed points like that last example. I've never really seen that last one show up anywhere on AP exam. You might see it on your homework tonight. Usually it's these two that we're a little more concerned with. So it is a case where the limit doesn't exist, but I've never seen it show up. All right, so you can pause that if you want to jot those last ones down, but that is our first lesson and first intro into calculus. So we've learned two ways to evaluate limits. We've talked about what a limit means, and we've talked about when limits don't exist. And those two ways of finding them are from a table and from a graph. Next class, we'll get into kind of the analytic ways, the algebraic ways of finding a limit. Okay. All right, so I want you guys to work on that homework. Make sure you guys are checking your answers and trying to get to the back of the book answers anytime you can.